model soil organic matter calculator that I put together in an Excel spreadsheet. And I said, I'd like you guys to write a grant to the Michigan corn growers, and I need some help finishing this model. And after an hour of presentation down at Bowling Green to the two of them, Rafiq got so excited I thought he was going to fall off his chair. And with that, Randall helped him write a grant, I believe, to the Michigan corn growers for $30,000. They hired a grad student named Vinayak Shetakar, whose Excel spreadsheet skills are much higher than mine. And using Visual Basic, he came up with a farmer-friendly soil organic matter calculator. This calculator has since been delivered to the Michigan corn growers, along with the user's guide. If you are a Michigan corn grower, you can access it at Piketon at the South Campus of Ohio State now, using a special code provided by Rafiq. And you can do actual field soil organic matter planning in a quantitative manner. Up till this time, most of us have dealt with qualitative models, such as the soil conditioning index, which kind of gives you a positive indicator that you're building soil organic matter. If you do follow this tillage system, or you change the crop rotation, or you add cover crops. But working back and forth with Vinayak this last year, we've had a lot of emails back and forth, and a lot of different versions of this model. We put it together so it looked like a conservation planning tool. Imagine that. So you can answer the questions, what if? What if I add manure to my crop rotation? What if I change my crop rotation? What if I add cover crops to the crop rotation? What will that do to the organic matter content in my soil 40 years from now? And if you know the soil test that you have in front of you, if you have the producer's cropping rotation and his yields and his soil test organic matter, it will predict what that's going to do in less than a minute. How cool is that, huh? And the whole idea of this is so that there's a lot of interest in cellulosic ethanol. Michigan State, there's a group of researchers there that got $1 million grant, I believe, to work with crop residues to turn them into fuel. Well, the bottom line is, farmers want to know, okay, yeah, I can sell some of my crop residue, but what is it going to impact my organic matter? This tool will help answer that question. So with that, I'm going to show you a little bit about something about the soil organic matter calculator that I've been working with the corn growers in Ohio State.
How far does your projection go, Ed?
What's that?
How far ahead does your projection go?
Well, we can reasonably predict out 50 years, but Vinayak took some of the Morrow plot data that goes back 100 years, and he's got a correlation of 92% statistically. And if you know anything about statistics, that's damn good. That's where all the dots fall on the line. So we don't know the limitation of this model yet. We're just scratching the surface of what it can do. We don't know the range of it. We don't know the robustness of it yet. But when we get an opportunity to find some money to hire another grad student or hire Vinayak to evaluate some of the other research data that's out there from places like Minnesota and North Dakota and Missouri, we'll start to realize the potential and the robustness of the model. But right now it's been basically tested with Illinois, Michigan, and Ohio data as far as I know. So the goal of our model is to maintain soil organic matter. And as I stated earlier, there's very few tools out there that quantify soil organic matter changes when crop residue is removed, such as baled up and made available for biofuel. It's the nation's most precious resource, soil organic matter, and I think Don Rakowski would agree with us on that. It requires 4,000 to 6,000 pounds of crop residue just to maintain the soil organic matter. And this depends on the soil, type, tillage, and climate.
That's a per acre.
This is the goal that Don Rakowski was trying to get us all to realize today, that instead of being conservation planners that just managed our soils for T, we need to go the next mile. We need to go the next step. We need to manage for C, not just T. And we need to substitute C for T in erosion and soil quality control if we were going to have healthy, productive, sustainable soils. In 2011 at the American Society Agronomy meeting, and you might recognize some of these three amigos, I'm one of them. The other one's Jerry Lemonnier and Bill Kunstler. CCAs were asked that attended the meeting, and there's a lot of, as Don would say, cabbage heads at this meeting. Not necessarily the practical people that are out on the land every day working with the farmer like yourselves, but more the scientific theorists that are working on futuristic models and such. CCAs asked them, what's the bottom line? You know, you come here and make all these presentations, but the farmers always ask us as consultants when we go around and sit around the kitchen table, how is this going to affect my bottom line? And that's back there shaking her head. Because guys are always coming in our office and says, where's the money? Right? Y'all been there. Where's the money? So how does selling residue for biofuel affect my cash flow and soil organic matter health? Well, how are you going to answer that question? What is crop residue worth? Any idea what crop residue is worth? Now, those of you who heard this talk, don't say nothing. Harvest efficiency is about 50%. This comes from MSU. The people that are doing the cellulosic ethanol work have said that they went out and harvested corn stalks, and they're able to collect about 50% of the surface residues out there. Not much more than that. And when we look what the nutrient value is of this residue, I took what the residue removes in pounds per ton and multiplied it by the amount of money in today's fertilizer prices that it costs for a pound of N, a pound of P2O5, and a pound of K2O. And depending on the type of residue, it's anywhere between $20 and $40 an acre per ton of residue removed. So just for the residue. Now that don't include, like June would say, the other partial budget items. It don't include baling up the residue. It don't include the fuel you got to spend to bale up the residue. It don't include the fuel you got to spend or any storage you got to pay for storing the residue. So you'd have to add that in there as well before you could break even. So just the nutrient value alone of a ton of residue is between $20 and $40 a ton, depending on the type. So if you're trying to grow residue for bioenergy, our goal, if we're going to manage for C, as well as for T, as Don talked about, is we've got to somehow get our soil organic matter gains to equal our soil organic matter losses, so we're not depleting the soil organic matter in the soil. So somehow we've got to add enough carbon back into the soil from other sources, either from residues, or from manure, or from a change in the crop rotation, or maybe by irrigation. How could you do it with irrigation? How's irrigation fit in the equation?
Push up the yield.
Higher yield, more residue, okay? So these are the things we can look at with this model to tell us if we take this much residue away for biofuel and we make these changes, what will it do to our organic matter in the long term? So there's some of the alternative sources we just talked about. And the founding fathers of this model were a couple old farts like Don Rakowski up here. Bob Lucas, I can pick on him, he's from Minnesota. And David Jenkinson. Bob was a soils professor at Michigan State. And Jenkinson was a world-renowned carbon modeler out of England. He worked at the Rothamsted Research Station, did a lot of work in his earlier years on coming up with the decomposition curve for residue and relating it back to soil carbon. I got a meeting with them in 1991, and they talked about this model they were proposing to develop to quantify carbon. And when Jenkinson related to Bob that it didn't matter where he went in the world, that when you put a certain amount of residue on the soil surface, after a certain amount of time it decomposes down to about 8% that goes into the old pool. Didn't matter whether he was in Nigeria, or whether he was in the tropics, or whether he was in Nebraska, or whether he was in England. The old pool was about, when you start out with this much residue, about 8% ended up in the old pool. The only difference was how rapidly it got there. And that related to soil temperature, moisture, and length of growing season, okay? In the tropics, it gets there a lot quicker because you got microbes working 24/7, 365. But in the Arctic, it takes a lot longer to get there because you have a short window of time that the residue's being decomposed. But ultimately, using carbon-14 radioisotopes, this carbon ends up becoming about 8% of the old, what we call the old pool, or Rafik referred to it today as the passive pool. So, using that thought, I saw Lucas in an Edison moment, I call it, and it was something to really see. You could see the old man's eyeballs light up. He says, I see carbon now in a little different manner than I've been looking at it. He developed his own carbon model, but he'd been working on it for 30 years. He worked on minority studies on campus and such. He says, I see carbon in a little different manner than I've been looking at it. And out of that came a two-pool explanation, little decay model that uses plant residue equivalents. It uses 6 pounds of residue to yield 1 pound of active carbon. Remember, earlier I said it takes 5 to 7 pounds of residue to give you 1 pound of active carbon. Bob took the middle of the road. He used a 6-to-1 ratio. Now, and he called it plant residue equivalents, so that he relates all carbon sources back to plant residue equivalents. Well, how does that relate to the models you guys are used to working with today? What do you use in the wind erosion equation? WEQ, for residue. What do you use? Small grain equivalents. Bob did the same thing with organic matter. He normalized his model by taking things back to plant residue equivalents so that he could predict the amount of carbon from each source. He used a couple long-term studies at Michigan State University he'd been doing with 10, 20, and 30-ton manure. And he developed this model using that long-term data that he had from the Beaten Bean Farm in East Lansing. And he divided his organic matter into the active and the passive pool, or in his paper he called it the new and the old. The new was the active, that 5% that Rafik was talking about earlier in his presentation. The old, or very dead, has been referred to as the other 95% that's out in the soil. So using this money for the corn marketing program, we come up with user-friendly software to predict soil organic matter based on what I call the Lucas model spreadsheet that I put together. And out of it comes some management guidelines that you can give farmers if you run the model for them, saying if you do these things, here's what your organic matter should be in 40 years from now. So let's see how the model works real quick. Again, it's an Excel spreadsheet. We went through several versions. Visual Basic was used to program it. You younger folks probably know more about that than us older folks. That was above and beyond me, so I was glad that I got to meet Vinayak's from India, but he's been a biosystems engineering Has he got his PhD yet? Did he get it? Is he a doctor now? He was working on his doctorate. Randall had him in his class and hired him wanted to know if he's interested in working with me on this spreadsheet to make it better. And he said, yeah, we had too much fun doing this back and forth. And I don't think he got paid enough for what he did accomplish with the $30,000 that corn growers spent, because I know he spent a lot of extra hours trying to get it to where it is today. He's on version 1.5x.
But that's thanks to Michigan. Michigan corn growers are paid for that program. Thanks to you.
So it starts with a simple data entry form. You can pick your simulation period, let's say 2012. And if we want to look at a 50 years simulation, I don't, because I'll be dead by then. 2062, some of you young folks might still be around. You can save the years. I'll be part of the dust. And then, if you know the grower's crop rotation, we're going to use just a simple continuous corn to start with, okay? Just to show you the robustness of the model. And let's say he's got 120 bushel. Now, one of the limitations of the model is you can only use one tillage type. You can't mix up tillage types yet with the model. Is that correct, Rafiq? Yeah. And even if you do put a till with a no-till, what's going to happen to the carbon that's been stored by the no-till if you till? Don told you this morning. It's going to go poof, huh? You get it blowing up, disappearing, shrinking, I don't know what all, but anyway, it's gone. Okay? Sure, it's going to go away. So let's just go conventional tillage for now. And one of the options you can use in the conventional tillage, if you remember from one of the slides this morning, the depth of tillage in Don's presentation made a difference in the amount of carbon that was sequestered, or lost, I should say. So you can put the tillage depth in there if you want to. You can use manure, and there's all the different manure types. And there's 18 different manure types you can select from, and you can put the rate that you're going to put on per acre. We're not going to do that right now. We're going to just do a simple calculation. You save and go to the next crop if you want to, or you can say done. Yes. Click save button. Okay. Now, if you have a soil test, okay, how are we doing? Won't let me go over here.
I think that would say six.
Oh, they did. Then done, okay. I thought it did, but I must have missed it. Thank you. So, let's say you start out with a depleted soil, say like on an eroded side hill. Say with like 1.5% or 1% organic. Let's say 1% organic. So you enter in 1% of it. Yep. And the other thing, your sampling depth, if he's shallow plowing, it'd probably be 0 to 6, so you can change that. Now the decay rate. This is a question that the farmer's not going to have to answer, but you as a consultant is going to have to answer. So most people don't understand the decay rate. The user's guide explains it more fully. There is a user's guide with this and it talks about it. But to help you, there's a little help screen. See that question mark? You drill into that, and if you don't know the decay rate, it gives you some guidelines on what decay rate to use. So, in this case, what soil type do you want to use today? A loam? Since we have a lot of loam floating around in here. Slaking and everything. So let's use a loam. And at 6 inches of tillage depth, we'd use a 2.5% decay rate. So we go in here and put 2.5% in. Oh, I think I hit the wrong key. Let me go back. 2.5. Enter. Now we're done. And at this point, we're ready to calculate it. This is a KISS model. Keep it simple, stupid model, okay? Because that's the way I wanted it. But there's a whole lot of math going on in the background that you don't see. So we're gonna hit the calculate. Yeah, okay. We're not gonna change any scenarios. There's a way to test it. I click OK. It's already calculated. And there is the form that you get after you calculate. And there's a graph that prints out. And it shows with that yield, at 1% organic matter, if you maintained 120 bushel yield over the next 50 years of simulation, your final resting organic matter would be about 1.8%. So that's kind of how it works. So let's see what happens. Let's do some what-if stuff. Remember I told you this thing can do what-if stuff. Let's show you how the rest of the model works. Real quick. You want to stay for the rest or not?
Yes.
All right, yes or no? You can go if you want. All right, let's go back. I'm gonna get back to the, I don't think I'm seeing this button I want to see. Let's look at the report real quick. It gives you a report. And here, it's partitioning. Remember we had said that there's the new organic matter and the old organic matter. It's partitioning that residue. It's showing it's producing 9,000 pounds of residue in a year. This much is going in the organic active pool, and then a certain percent, 8% is going into the old pool. So that's why you see the old pools steadily increasing over time, and that's changing your organic matter over time. Remember, it's a two exponential model. So it's decaying the old organic matter, and it's constant, 8%, but it's adding active organic matter in an exponential fashion over the first 5 years, and a certain percentage of that keeps going into becoming the old pool. Okay, how do I get back, Rafiq, to the input? Oh, and then there's this cool graph it prints out too. I love this graph. It shows the old pool, which by far is the biggest part of it, and it shows the active pool, and it shows the total organic matter. It shows what's going to happen to it over time. Gotta get back to the input book. We have to just close this, maybe?
No, you can,
There's a way, but I'm
you
not.
can change the.
Oh, there it is.
Yeah, tillage.
Okay, there it is. That's what I was
No,
looking
you
for.
can,
I'm good.
conventional tillage, you can go say no till.
Yeah, let's go to no-till,
Very good, no till.
and then now let's calculate. So Rafiq's changed it to no-till.
When you want to input scenario.
You gotta
across those
calculate though,
lines-
don't you?
Yeah.
You don't you have to do it in the data entry form?
Oh, okay.
No till.
Let's go to the data entry form, put it in there. That's where I've had my best luck.
Okay.
We'll just do it over. It seemed, yeah.
But I do it in
Yeah, 2052, 62.
62,
Yeah, save your years.
and corn.
Corn. Use corn. Yeah, so use the same. I've changed the tillage to no-till. Okay, and we're pretty much done. Save it, save it, you gotta save it. Save it, then say done.
1.5 or what?
One, we was using one. Decay rate was 2.5.
No till.
2.5, and we had a 0 to 6. There's a way to skip this and save scenarios, but we're not going to show you that today. I'm just going to show you the quick version here for me.
So if you were previously no-tilling, your old organic matter decay rate was different, is that correct, Jerry?
Yes, from what we can see looking at the data, that's different, and that was one of the things that Ohio State brought to the table that I didn't
This
have.
one is
Michigan
more than
State,
2%.
they had 40 years of no-till research data they could bring to the table and help me find out what that decay rate should be. because Michigan State didn't have that.
Then cover crop, say no till.
Well, let's show the outcome of what you just did.
Oh, we already did that, we already
Did
showed.
you see?
Yeah,
You
so,
see it went up, with the no-till, it went up to 2%. It went up higher. Okay, now let's add manure. Let's add 20 tons of manure, yeah.
or say cover crop.
Okay, cover crop too. What are you gonna do? Rye, well, cereal rye would be practical.
Look at that,
Where did you just add that?
We just added cover crop
Oh,
in.
over on the side, I'm sorry.
look at that, without cover crop, that, I'll do it again. Look at here, 2%. I just add cover crop,
Annual rye, yeah.
look at that.
Now we
almost
went to
3%.
almost 3%, just by adding the cover crop every year.
And if you add manure, then it will change.
And if you add manure, it'll do the same thing. It'll go up again. So
If you
you
add,
can show how you can increase your organic matter over time. And then there's also a place, where do you remove the residue?
yeah, okay, if you add,
Somewhere to remove the residue
yeah,
here.
if you remove the residue, say
Now, if you want to sell some residue, you can
30%.
go in here and put in how much you want to sell. Probably 3,000.
Say 30,
Or, if I said 50% was a maximum, if you wanted to do that. Or 30, either way.
oh, here,
Yeah, here, okay.
sorry.
It's okay.
And look at that, if you sell the, it decrease. And if you sell 30% of your crop residues as
And
energy
grow a
stock,
cover crop and use no-till, and you're still gonna increase your organic matter. So that's the robustness of the model.
and if you add soybean or wheat in the rotation, you will see tremendous effect.
We will be presenting this next week at the American Society of Agronomy. Rafig's put together 5 papers that are gonna be presented there on the validation of the
Yeah.
model.
You can
So
print the
at the end
name
of my
of the,
career, this is a very exciting time. To
yes,
see something that I've worked on for 20 years
you
come
can,
to where, something that maybe you'll be able to use soon.
you can write the
Is there a
name,
summary or something
location,
you can share with the farmer versus?
and
like,
not only that,
numbers and,
Remember when, Jen, we had $30,000. With $30,000, we took it this far, and those were low paid per hour dollars. When I probably got less than minimum wage to get it this far, okay? He put a lot of hours in to get it to here.
right? I'm just
Now the
thinking
goal is to find some more money, to hire Vinayak or somebody like him, to work with him further and put together a summary page like you're talking about. Him and I have already had this discussion,
Yeah, usefulness to the
but
farmer.
I gotta find the money,
Yeah, I know.
okay?
here is the summary, you
He ain't
can,
gonna do it for nothing.
Oh, he's got a summary there.
you can discuss the summary, it will tell you the organic matter content.
But we were talking about like a one-page summary, like
And then
from
if
our,
you
we
remove
got
residue, it
15
will
fields
calculate,
type thing in one page.
and how much nitrogen you accumulate.
Well, that'll be easy to do, it's just a matter of putting the dollars together to do it. I already talked to Vinayak about it, he said, yeah, I can do that.
Yeah, how much nitrogen you can accumulate,
And also the
how much carbon you have
carbon,
to
how much carbon is
sequester,
being sequestered.
and then what, this, we are still working, the recommendation, what needs to be done. If it is really bad, what needs to be done, or if it is good, what needs to be maintained. But the good thing is, again, Michigan provided 30,000, not only that, I provided money from other guy, so that guy. But the initial money came from Michigan, yes, thank you for that money.
So that's the organic matter calculator.
Hey, Jerry, any idea when this is gonna go out to us, or?
Well, it's available at Piketon at the South Ohio State University campus. They put it up on their website, and Michigan core growers can access this calculator for free. I was talking to one of your helpers in your office, and I'm gonna get her the code so she can come down and show her, work with her on it.
Perfect, okay, thank you.
There's a code already given to them. If you use the code, then you don't have to just enter the code, otherwise you have to pay some money to maintain that website. But this model, what Jerry initially started, is not the end. We are putting phosphorus fertilization, nitrogen fertilization, water quality, irrigation, liming, all these pages will be added. So it will be a robust model ultimately.
And we're hoping to generate some enthusiasm for it next week at the ASA meeting, so the money comes in. Okay, that was my presentation, basically. Free to go.
Yeah, we need